We have been talking about uncertainty in measurement. And I know it's difficult when you're asked to calculate uncertainties and follow the rule of uncertainties to find an answer or whatever. It's difficult to focus on the greater, the deeper meaning, but it's the most important part of it. My science of physics is a science of measurement, of observation. What I'm going to do, what I want to do, the challenge of this, is to look at the universe and describe it. That description involves making the measurement of fundamental quantities that I must define, and then finding relationships among the quantities that we call physical laws. It's wonderfully exciting. I get to describe a whole universe. It's so much better than things that I do in social studies, for example. I might study it from time to time. I might study the Magna Carta, right? That was a very important document, whatever, but that's a human thing. It only exists here on Earth, and it only exists because of the terribleness of mankind. But what I get to talk about, the fundamental nature of things, the construction of the universe itself. I begin from scratch. I begin from nothingness, and that's exactly where I'm going to start today. I'm going to ask you to imagine a universe that is devoid of anything, a universe of nothingness, a true void, all of creation empty. Some of you who are neat and tidy and anal retentive might think, that sounds relaxing. An empty universe, empty of everything, including an observer to look at it. And so here I come. Here I am now. Whoa. Hello, universe. Looking around. There's nothing. Void. Except something really important has happened. Technically, two important things have happened. One, I am now the observer. I observe the universe. Two, I immediately decide that I am here. This location of the universe becomes special because this is where I am. As soon as I was talking about this, I remembered a thing that happened to me recently. My son was after me for a very, very long time for a virtual reality headset for the PlayStation. Dad, PlayStation VR, PlayStation VR, PlayStation VR. Just over and over again. No PlayStation VR, no PlayStation VR. Because he had seen it on the internet, people wearing the helmet that transports them to like a virtual world sort of thing. And he was really excited about that sort of thing. And he wanted. And I said no and no and no and no and no. For at least a year, the answer was always no. And then finally I decided that the answer would be yes. So I went and got it in secret. Wednesday is hamburger night, where we go out and get hamburgers. So there we are, we're having our hamburgers. And I say to Jakey, hey Jakey, guess what I have at home waiting for us right now? No expression whatsoever. He says, PlayStation VR? Well, yeah. I mean, if you want to take all the fun out of it, sure. So there, a short time later, there he is. He's got his virtual reality headset on, and he's looking around, and he's waving the thing. It's quite hysterical to see someone experiencing sensory input that nobody else can see, right? Waving around and running into furniture, and the cat runs away, whatever. All that's going on. And he was very, very happy about that, very excited about that. But of course, I tried it. So I take the VR headset and I put it on and I activate the thing, and suddenly, it's like the Matrix. Suddenly I'm standing in a void. Bizarre. But there are like a little bit of space, maybe some stars, some nebulas, a little bit of cloud of gas and whatnot. And I look down and there's a green neon grid on the floor, much like the tiles here. And my brain tricks me and tells me I'm standing on it. So there I am, I'm standing in my living room, looking around like an idiot going, whoa, neat, what? Oh my gosh, and looking around at a grid on the floor. And the reason why the grid is there is because in the absence of the grid, if you just take the VR headset and you put it on and everything's just black in all directions, you might as well be wearing a blindfold. That's not as funny as I thought it was going to be. You put the blindfold on, it's just blackness, you can't see anything because there's no reference. And so when I put the thing on to make it look really cool, they put that green grid there so I could have some sense of space. Because my sense of space, my observation of space, my understanding of space depends on a reference frame. And in fact, the reference frame that we typically use for three-dimensional space in our universe is X, Y, Z. There it is, the X-axis, the Y-axis, and the Z-axis in three-dimensional space. Three-dimensional space is going to blow my mind if I start doing physics in 3 dimensions. So what I'm going to do is I'm going to limit our discussion, for the time being, I'm going to limit our discussion to one-dimensional physics. One-dimensional, because it turns out after the fact that once you figure out how to do one dimension, adding the other dimensions on will be easy. So we'll simplify things a bit by starting with one dimension. So here I am in a completely empty, one-dimensional universe. But to understand it, in order to observe it, in order to measure it, I have to have some way that I can refer to space itself. Because here I stand at the origin of my coordinate system, and then all of the sudden, my empty universe is no longer empty. Blue towel. A remarkable thing has just happened. My universe has here, the location where I stand. My existence, my observation from here. It's a very egocentric universe, this. But then all of a sudden, blue towel. Where? That way. Oh, you mean this way? No, not this way. That way. Now all of a sudden I'm starting to think about it in the context of my orientation in space and direction. So what I'm going to do is a thing that was first done to you in like 4th grade. I'm going to describe this by drawing a line, because remember, my universe that I'm describing is one-dimensional. So I'll draw a line that represents this one-dimensional track that I live on here. In particular, there's a spot on this one-dimensional line that I specifically call here. Here is where I am. Where is the towel? It's that way. So I need to say, I'll put a little arrowhead on the end of this, and I'll call this that way. So very scientific. So very good. No, not this way, because this way is different than that way. They're different. They're distinct from one another. I can make a distinction that the towel is that way and not this way. Haha, now I've really got it. Now I can describe my universe quite well, because I can say, I'm here, the towel is that way, and there's nothing this way. Now something that was complete void begins to be fleshed out by a description. The trouble with this description for me is that this way and that way, they're not very distinct. They're not very distinct from one another. I have a problem with that, just using words like this way or that way. I need to be more, I'll be more specific. I'll make my description here better. So I'll draw it again here, right? I'll give it another try and try to be a little bit more scientific about it. You can't just say, I'm here. That's not the very good description. You know what we do? Just like we do in math class, we'll take a very, very simple idea and we'll make it more complicated by giving it a fancy word that nobody understands. Okay, so instead of saying here, I'm going to call this location the origin. The origin. So it's not about me. It's not about me being here. It's about the concept of here-ness. I love how deeply philosophical this whole physics thing is. Don't you, Matt? I get the thumbs up from Matt. Okay. And it didn't do me any good to call, this way and that way. That's a little bit silly. So let me be a little bit more official about it. It'll give it a better name. That's better, right? That's better. Do you like that? You do? What's the matter? Will's not so sure. What do you mean it's going the wrong way? The towel is on the left.
It's relative.
It's relative to the observer. It depends on who's looking. Does the universe depend on who's looking? Let me tell you a very romantic notion. A very, very romantic note. This actually was a thing when I was a child. It's funny, between my brother and I, my brother remembers nothing from his childhood. I don't know how you are about it. I think probably everyone's different. My brother remembers nothing about his childhood. I remember everything about my childhood. Memory's a thing that I have going for me, thank goodness. It's one of my favorites. I can remember as a child being at my grandparents' house until after dark, and being taken as a child and buckled into the back seat of the van. We had this busted ass van. It was unbelievable. It was my father refers to it as a window van. I didn't even know it had windows, but it was like primer and whatnot. And we'd go on vacation just by throwing junk in the back of the van and driving off into the mountains. I remember being buckled into the back of the van and driving home from Grandmom and Pop-Pop's house and looking out the window at the night sky and seeing nothing but blackness. But then as I looked, all of a sudden, I'd see a star, and then another one, and then another one, and then another one, and another one, and another one, and another one. And suddenly I would begin to see stars in the sky. And I remember thinking, what a curious universe it is that the stars don't come out until I look at them. Now, I'm just a little kid, so forgive me for how egotistical that is. But as a tyke, I believed for a time that the stars didn't come out until I looked at them. The stars didn't come out until I looked for them. Wasn't that ultimately true of everything? Our experience of the universe doesn't happen until we look for it. Have you ever had that experience? You look at the sky and you don't see any stars, but then all of a sudden you do? No, you've never had that? No. You should go outside and look up. Not now. Okay. Wait until dark. And then that observation of the universe, that the stars only come out when I look for them, As I get older and I have more experiences, that becomes a more sophisticated observation. I realize that what's happening is my eyes are adjusting to the light. I was just inside the house where the lights are very bright. And when I go outside, now I'm in the car. Now my eyes adjust and the sensitivity to light increases. And then I begin to see the stars. And then I realize that the stars are there all the time. And then later on, I realize how stars are defined, how they're constructed, how they're regulated, how the gravitational pressure and radiation pressure determines how, the stellar evolution. Right? And I get my description of the universe becomes more and more sophisticated. So I take this egotistical idea of here, and I replace it with the idea of the origin, and then I replace this way and that way with left and right, but it doesn't work because it's not objective. We should all observe the universe the same way. It's the same thing as saying that you should measure the table and everybody should get the same result. It's the same thing as that. We should all make the same observation of the universe. And when I say that the blue towel is on the left, you look at it and you say, no, it's on the right. We don't agree. So my description here needs to become even more sophisticated in an objective way. And that objective way is to draw my line, and instead of writing left, write an objective symbol that we will agree on. I will draw it, you will see it, we will agree as soon as I draw it. And that is, I will call this plus, and I will call this minus. And I will call this something different in just a moment. They say, oh, no, Scheidly, I get it. I see where you're going. It's going to be a number line. Positive numbers, negative numbers. Well, that's what it was in 4th grade when they were teaching you how to count, how to add and subtract. And they did it by drawing a line and saying, this is the positive and this is the negative. But what I've done is I've created a direction in my universe that I call positive, and a direction in my universe that I call negative. And you agree, don't you? That now the blue towel is in the positive direction, but you could not have agreed without me first declaring it. You see, the declaration is important. The declaration is important. I have to say. Well, that's wonderful. That's wonderful. But now we're done. There's nothing else we can do. The blue towel is in the positive direction. There's nothing in the negative direction. I'd like my universe, or my description of the universe, to be more sophisticated, however. Because maybe there's more than one thing in my universe. Maybe there's the marker. Oh, now there's the marker. Now I need to describe that. Well, you see, the marker is closer, and the towel is further. What does that mean? It's a really quirky thing about our observation of the universe. Check it out, Nick. You're there. I'm here. What the hell does that mean? Well, a thing that I've mentioned before in class many times is that space itself is defined in the context of its measurement. Space is kind of meaningless until I measure it. So what I'll do is, standing here at the origin of my coordinate system, I will choose a standard of length, the meter. And I will lay that meter down. And using that meter, I will mete out tick marks. And those tick marks will each represent a meter. As soon as I do that, I can say that the marker is 1 meter. Positive 1 meter. Oh, that's very good. And the towel is positive 2 meter. Now they're distinct from each other in a way that I can quantify by measurement. Because measurements quantify observations of the universe. Hot damn. So what I'll do is I'll replace the name of the origin. I need my marker back. It was not a good idea to use the marker as an event or phenomenon in my universe. I'll replace the origin with 0. The origin of my universe, 0. And I'll flip my meter stick end over end, and by the way, with whatever precision I can manage, millimeters, or do something with a caliper or something like that, whatever sophisticated measurement I can do to increase precision. But all of these tick marks, uncertain, one after the other, meters. 1, 2, 3, 4, 5. Scheidly, it is a number line. It most assuredly is a number line. Most assuredly is a number line. That is, it has a positive side, a negative side, and I'm putting numbers on it. Scheidly, you're completely ignoring the negative side. Oh, I feel terrible about it. I feel terrible about it. So, of course, I will also mete out tick marks on the other side of the number line. 1, 2, 3, 4, 5. Oh, I've caused some confusion. Because I have meters 1, 2, 3, 4, 5 on the positive side, and I have meters 1, 2, 3, 4, 5 on the negative side. You know what I'll do? I'll mark them with a negative. -1, -2, -3, -4, -5. I have created a number line that allows me to absolutely define the location of the towel, blue towel there, in the universe. Positive 2 meters. Scheidly, you're so foolish. What if you put the 0 over here? Now it's positive 3 meters. Like, that position doesn't really mean anything. You're right. It doesn't mean anything unless I define my number line right at the beginning. We're not going to call it a number line. We call it, in our physics, a coordinate system. The coordinate system is the framework whereby my measurements of position are defined. The coordinate system is the framework, and it has to be defined. Not just in the first physics course you ever take, but if you go on and become a physicist and do the fanciest physics that currently exists, you cannot define measurement without first defining where is zero and what direction is positive. You cannot define without choosing where is zero and what direction is positive. The choice is arbitrary. You can put it wherever you like. It's completely arbitrary, but you have to choose, because without the choice, there is no such thing as our first physics quantity ever. Our first measured quantity in physics, which is given the symbol x. It's given the symbol x because it's familiar to things that we've already learned in math. It's kind of traditional to call it x. But I've already referred to it as position. I am not a fan of writing long sentences on the board, so I'm just going to say it. And I want you to think about what it means and appreciate the fact that you already understand quite deeply what I'm talking about. Position is the location of an object or an event relative to a coordinate system. Position is the location of an object or an event relative to a coordinate system. It's where on the number line. It's where on the coordinate system. There's a thing that I'm going to do in all of the physics that we do from now on. I'm going to make a bracket like that, a little square bracket, and in it I'm going to write the units of a quantity. And I'll do that when I define new things in our physics. I'll write position and put a little bracket there and say m, because the SI unit of position, of course, is the meter. The SI unit of position is the meter. And so when I write positions, they'll be measured in meters. Very, very simple, in fact. So now I can locate every object in my universe. All I have to do is choose origin of the coordinate system, that way positive, and now I look around and I want to describe my universe, and I describe it in the context of the only physics quantity that I have, which is position. Everything in the universe has a position. Everything. And so I check all the positions relative to the coordinate system, and I write them all down, and there are all the positions, and now I'm done describing my universe. It is over. It is complete. Lovely. So I'll just close my eyes for a second and take a rest. Well done. Good physics. And then I open my eyes again and I look around, and much to my delight, I discover that so many things in my universe have changed their positions. That's what's lovely about our universe, and as it turns out, necessary, that everything in the universe can change positions. Everything doesn't stay in the same spot. In fact, everything changes. Everything changes. Everything changes. It's a universe of change. Nothing happens without change in position. And it turns out, really, when we get down to it in the final analysis, there is no such thing as standing still. There's no such thing. Standing still is a problem of definition in our universe. There's no such thing as stationary, as still, as unmoving, unchanging. No such thing. We live in a universe of change. And so I locate the positions of everything in the universe, and then I close my eyes, and I open them again, and everything's someplace else. Then you get upset about that because you had everything all figured out. You knew what all the positions were. Or you can go, ooh, that's interesting. Let's examine it. Over here I have an object, and the object was at 2 meters. Now it's at 1 meter. It changed its position. It's quite remarkable. But I look over here, and there's a thing that was at negative 50 meters. And now it's at negative 1 meter. Oh my goodness. That was a great change in position. Well, this is a small change in position. Apparently, changes in position can be distinct from each other in terms of their magnitude, the greatness of the change in position. Some things change their positions a little bit. Other things change their positions a lot. I need to create a new physical quantity that describes the change in position. I need a quantity that describes the change in position. And this is going to give you your very first physics equation ever. It's exciting. The change in position. X is the symbol that I use for position. The change in position I'll write as delta X. In all of our science and engineering, delta traditionally means change. Delta X. The change in position. That's what delta means. Delta capital T, change in temperature. Delta capital B, change in magnetic field. Delta opinion, change of opinion. Delta means change. Delta means change. And I get to define it. I get to define. Scheidly, you're just making it up. Yes. Are there alternate ways to define it? Yes. This is the way we do it in our physics, the physics of humanity. the physics of this universe. The change in position is by definition the final position. That is what the position is right now. The final position, the position after it's changed, minus the initial position, x naught. Scheidly, x sub 0, technically it's not a 0, it's a naught. And you have to say it with a slightly British accent. X minus x naught. That's too much British accent. I got to dial it back a little bit. X minus x naught. Final position minus initial position is displacement by definition. Scheidly, why? By definition means I just made that up. Well, I hope it's useful. Well, yes, very much so. Thank you. The change in position, delta x, is called displacement, which is a word that you may have already heard in your everyday language, what we call colloquial. Displacement, right? Like folks used to live over here and now they live over there. Displacement, change in position. So it's a word that you already knew. Displacement, the change in position. And it's the first physics equation that you have. It's the very first physics equation that you can use to calculate a thing from measurements that you make. You measure the position, the position's different, you subtract, whammo, displacement. Whenever I come up with equations for our physics, I'll put them over here in a list of useful things. And immediately a question crops up among students. I'm going to tell you the answer right now. Scheidly, do I have to memorize the equations? Yes. For years and years, we've been providing students with lists of equations, and it's always frustrated me. So now I'm saying, yes, memorize the equations. And part of the reason is I'm not extremely excited about the level of physics that I've been getting from students in the past few years. And so I'm hoping that by, you have a grumpy look on your face about it, I'm hoping that by memorizing the physics equations that you'll interact with them in a more deep way, and hopefully it'll improve your success at solving physics problems. That's my equation for displacement defined this way. Scheidly, I really think that I should solve an example. Excellent. Here it is. An example of calculating displacement. I have a cartoon character that I use whenever I'm making up example problems about physics. His name is Slim. Slim is a stick figure, and in this example I'm going to provide Slim, and here's Slim, stick figure guy. Slim is going to run a race. You may wonder, poor Slim, he's the subject of all of my physics problems and whatnot, Slim is a dude. So maybe you think, well, that's a little sexist, Scheidly. Slim. No, Slim has a wife. Slim has a wife. She shows up periodically. Her name is Peg. She also is a stick figure. They have a son. His name's Twig. Twig has a pet horse, Matchstick. So here's Slim. Slim's going to run in a race. And the race is kind of curious. It's one of those things where you just spontaneously, I bet I'm faster than you. And so it starts here, where Slim happens to be standing here at the beginning of the race. So I'm going to put a little sign here, a little sign like driven into the ground, like a little wooden stake sign like that, and it's S, the start of the race. And the rules of the race are, you have to run all the way down there to the old tree. You have to run down there to the old tree. And the old tree, as it happens, here it is, the old tree happens to be 80 meters away. There's the old tree. A little bit of art. And the old tree happens to be 80 meters away. So from the starting line to the tree is 80 meters. From the starting line to the tree is 80 meters. And then from the tree to the finish line is actually further than where the starting line was. Here's the finish line. I have to put a little caveat on here. This diagram not drawn to scale. But here's the finish line over here. And I'm going to say that the finish line is 100 meters from the tree. And I'm given those quantities in the description. My question is, if Slim runs the race from the starting line to the finish line by running to the tree and then back to the finish line again, what is his displacement? You say, oh, Scheidly, no, I know. It's 100 meters minus 20 meters is 60 meters, is 20 meters. You have to be careful, because there's a temptation among physics students to read a physics problem and then just grab numbers and jam them into an equation and start solving. I have to do it in a more intelligent way. So I'm going to calculate the displacement for Slim by applying this equation for the displacement that I've written here. How do I calculate displacement? Final position minus initial position. But my problem here is I have not yet chosen my coordinate system. I have not chosen the coordinate system in which I make measurements of position. These numbers that are given, they're just the distance from the starting line to the tree, from the tree to here, whatever. They're just the distances that are given. I have to choose a coordinate system in order to measure the positions. And the choice is arbitrary. I choose. I can put it wherever I want. I can put it wherever I want, and I'm going to get the right answer. So what I'm going to choose is I'll choose to put the origin of the coordinate system here at the starting line and draw that as the positive direction. This is a little icon I like to use that indicates my choice of coordinate. It tells me where 0 is and what direction is positive. And I presume then, and I make it like a number line by putting tick marks on all the meters this way and that way. So there it is. When I write it this way, when I choose my coordinates like that, what is Slim's initial position? 0. Because he starts at the origin of my coordinate system. Scheidly, but 100, I don't care about 100. I don't care about 80. What is his position in my coordinate system? I'll be honest about that. His initial position is 0. So when I'm calculating his displacement, delta x is equal to the final position minus the initial position. It's minus 0. The initial position is 0. What is Slim's final position in that coordinate system? Negative 20. Because positions can be negative. I can't just take 20 and jam it into the equation. It is negative 20. So his displacement is negative, or his final position, that's what I meant to say. His final position is negative 20. So his displacement is negative 20 minus 0 is negative 20. Negative 20 minus 0, negative 20, and of course the units of that are meters. I neglected over here to write that since, of course, the positions are measured in meters, then the difference in positions, the change in position, would also be measured in meters. His displacement is negative. How should I interpret displacements that are negative? Because I can have positive displacements, it can be positive. How do I interpret a negative displacement?
It's like direction.
The negative sign is direction. Well said, perfectly realized. A negative displacement means I changed my position by 20 meters. In the negative direction. I changed my position by 20 meters in the negative direction. That's what the negative sign means. We say, Scheidly, that's all well and good, but you chose the coordinate system arbitrarily, Scheidly, you just made that up. Okay, let me choose a different coordinate system, solve the problem again. Let me choose the origin of my coordinate system to be the finish line instead. Let it be the finish line instead. When I do that, let me calculate the displacement again, new calculation, delta x here. When I do that, what is the final position? 0. What is the initial position in this coordinate system, right? Because from the origin here, how far to where he is, that's 20, positive 20. So final position of 0 minus initial position of 20 is negative 20 meters. Do you see that the choice of coordinate system does not matter? And of course it can't. The observation of the universe can't depend on how you look at it. The observation of the universe can't depend on how you look at it. So the answer is independent of coordinate system, but I can't get the answer without choosing. I can't get the answer without choosing. Notice that in my calculation, I did not use 100 or 80. Which technically you did because you had to subtract in order to figure out what the positions were. That's true. But if I do not respect the definition of displacement, then I'm in danger of misusing displacement whenever I use it to do a calculation in the future. And it turns out displacement, as one of the most fundamental measurements that I can make in physics, is going to be critically important going forward.